Hello and welcome back. So this video is for class 12 and we will continue with moving charges and magnetism. Now today we will see the concept of moving coil galvanometer, which is the last theory topic. Okay. Already I have shared the numericals, the solved exercises in the group with you. So go through all these numericals. If there are any specific numericals you want me to solve, you let me know in the doubt section. Okay. So in the next class I will solve only those numericals. I don't think that will be a problem because all the numericals are very straightforward in this chapter. Okay. But anyways, go through them. If there are doubts, you ask me. And then now let us start with the with today's topic, and that is moving coil galvanometer. Okay. So now galvanometer, that is not a new topic for us. We have seen the working of the use of the galvanometer when we were studying about potentiometer and about Wheatstone's network. Okay. So there are different types of galvanometers. We can have an astatic galvanometer or a mirror galvanometer or a tangent galvanometer, okay, or a moving coil galvanometer. The one that we use mostly, that is the moving coil galvanometer. Okay, it is a very compact structure and it is very easy to use. Okay, even in our lab we will be using the moving coil galvanometer. So today we are going to see the structure and the working of this moving coil galvanometer. We know that a galvanometer is a very sensitive instrument, okay, and generally it is used to detect even a small electric current present in the circuit. So even if a small current is going in the circuit, okay, the galvanometer will be able to detect it. But there are some more uses of the galvanometer. We can actually use our galvanometer to measure the electric current, okay, and also to measure the potential difference. So that is also what we are going to see in this topic. Okay, but first let us talk about the construction of the moving coil galvanometer. Now, as the name suggests, moving coil galvanometer means it is going to have a coil which is moving. Okay, so basically the understanding is if a current will flow in the coil, it is going to move. Okay, as we have seen in the previous topic, if we have a current carrying coil and it is placed in a magnetic field, there will be a torque acting on the coil. Okay, so that is basically the concept that we use in making moving coil galvanometer. Okay, so generally this is what a galvanometer will look like. If we open it up, inside this is what we will see. Okay, so now what do you see in this diagram? First, there is a coil inside. It is a rectangular shaped coil with many turns of insulated copper wire. Okay, then this coil is placed around an axle, okay, so that it can freely move. Then that coil is placed between strong magnets, okay, and you can see the shape of the magnets is concave, right? That is so that we can get a radial uniform magnetic field. Okay, that is one reason. Second thing, inside the coil we put a soft iron core. Okay, again the function of the iron core is to create a radial magnetic field for the coil, so that when the coil is moving at all times, the direction of current is perpendicular to the direction of magnetic field. Okay, so that is a question sometimes asked in the exam, that why there is a soft iron core inside the coil. Reason is that to maintain a uniform radial magnetic field inside. Okay, and then of course the coil is attached to a needle. Okay, that needle can be then calibrated on a scale where we will be able to make the measurements. So let us try to understand the construction. So imagine it is a coil like this. Okay, it is a rectangular shaped coil and there are many turns of this coil. Okay, so and then inside the coil there is a soft iron core and the coil is placed like this. Okay, that is inside inside a strong magnetic field, and there is the needle is attached to the coil. So if an electric current will flow in the coil, okay, there will be a torque acting on the coil which will make it to turn. Okay, and the twisting of that coil will make the needle to move, right? And you can see the needle is attached on this scale that will help us to make the measurements. Another thing, there is a spring that is attached on the coil. So what will happen is, because of the torque that is exerted by the magnetic field, the coil will turn and the spring will try to oppose that motion. Okay, so at an equilibrium we will get the torque that is applied by the magnetic field will be equal to the torque by the spring. Okay, so in short, that is the construction of the moving coil galvanometer. So now how does it work? So we have a spring, we have this coil, okay, and that is placed inside a strong magnetic field. So if an electric current will flow in the coil, correct, that will create there will be a torque acting on the coil because of the field. Because of that, you will see this needle will start to move. Okay, it will reach an equilibrium state when the spring is going to apply a force of reaction on that on the coil. Okay, and then it will stop, and we will see, we will get some reading for it. Okay, so now how do we find out the principle of this moving coil galvanometer? So here is the understanding. We know that the torque that is going to act on our coil, that will be equal to M into B. Okay, the moment, the magnetic dipole moment multiplied by the magnetic field. How much is the moment then? Moment is I into A. Okay, now how do you find out current? Let us say there are n number of turns of the coil. The total current will be n multiplied by I. I is the current that is flowing through the coil. So we will get therefore torque equal to capital N, capital I, capital A. This is M, okay, N into I, total current, multiplied by area. Area is the area of that coil, multiplied by B. Now you will see, we have not taken the factor of sine theta here. Why? Because the field is radial. So sine theta will always be equal to 1. Correct? That is why we have put the soft iron core. That is why we are having these concave shaped magnets. So that we always have sine theta as 1. So we get torque is equal to NIAB. Okay. This equation gives the torque that is acting on our the coil. Now let us say the spring constant is K. Okay, and then the coil has twisted by an angle of phi. So we can say the restoring torque will be K into phi. That should be equal to the torque that is acted on by the magnetic field. So you will get K phi is equal to torque, that is the torque, and this torque is nothing but NIAB, or you can say therefore phi is equal to NIAB divided by K. Okay, this is the relation we will get. So here is the relation we got. We got phi is equal to NAB upon K into I. Okay, we have just rearranged it and we have written it like this. Phi, that is the angle of twist, how much the coil has twisted by. Phi will be equal to NAB upon K into I. This is the same equation as before, don't think this is a new one. And what do you see? All the quantities inside the bracket are constant. N, number of turns of the coil, constant. A, area of the coil. B, the magnetic field. K, the spring constant. So this quantity in the bracket is a constant. Okay. What is variable? The current is variable. So what you can say therefore phi is directly proportional to the current. So we can say that in a moving coil galvanometer, the angle of twist is directly proportional to the amount of current. This is the principle of the galvanometer. Getting the idea? So depending on the amount of current, we will get the angle of twist. More the current, more will be the angle of twist. Okay, so that was the principle of the galvanometer. Now let us see how we can convert our galvanometer into an ammeter or into a voltmeter. First let us see for ammeter. So if we want to convert a galvanometer into ammeter, we have to attach a very small resistance in parallel to the galvanometer coil. Okay, why do we do this? Now technically an ideal ammeter should have zero resistance. Okay, so that all the current can flow through the ammeter. Correct? Normally a galvanometer coil might have a high resistance. So directly we cannot use the galvanometer as ammeter. Okay, so what we do? We take a small resistance. It is known as the shunt resistance RS. Okay, and as you see in the diagram, a small resistance RS is attached in parallel to the galvanometer coil. Okay, so what this does? This reduces the overall resistance of the coil combination, the combined resistance. So therefore, by attaching a small resistance, now this structure, this will act as an ammeter. Okay, the ratio of phi to I, that is deflection to current, is known as the current sensitivity. Okay, so that is how we can convert galvanometer into ammeter. Next, how to convert galvanometer into voltmeter. Now again, technically a voltmeter is supposed to have infinite resistance, so that no current will flow through the voltmeter and it will only measure the potential difference. So if we want to convert our galvanometer into voltmeter, we should attach a high resistance in series with the galvanometer coil. Okay, as you see in this diagram. So if we attach a high resistance in series with the galvanometer coil, then our galvanometer will now act as a voltmeter. The ratio of deflection angle to potential difference, phi upon V, is known as the voltage sensitivity. Okay, so this is how you can convert galvanometer into ammeter or voltmeter. So basically whatever analog voltmeters and ammeters we are seeing, they are modified versions of the galvanometer. Okay, now a detailed answer you will find in the notes that I have given to you. Okay, there are a few steps of how to make the connections and how that overall resistance will be affected, but of course that you will be able to understand from the notes very easily. So with that, the theory topics for this chapter are completed. As I said, the numericals I have already sent to you. Go through all of them. I am sure you will be able to solve most of them. If there are any specific ones that you need an explanation to, let me know. In the next class, we will solve those numericals and then we will start with the 5th chapter. Okay, thank you.